Hello and welcome back. So we are going to continue on with our topic 9 here by talking about antisymmetric properties. Um, so we've talked about three types of properties so far. We have the reflexive property, we have the symmetric property, we have the transitive property. So hopefully by now you have a pretty good idea of how to analyze each one of them. And definitely in the textbook, there's lots of examples on evaluating each type and being able to fully understand, what is a good counterexample for this property and when we can make a proof for such a property. Okay, so let's continue on with the antisymmetric property, which is the last one we're going to talk about. Generally, there are lots of different types of properties out there. So in your textbook, you're going to see many other examples of properties. I invite you to take a look at those types of properties. You won't be responsible for them on the exam, but it's good to know what other properties are out there. But let's talk about antisymmetric properties, and you're going to see why strategically we talk about these four, because there's these four are actually pretty important to something else that we're going to analyze a little bit later on. So firstly, what is the antisymmetric property? For all xy, xy and yx in the relation implies that x equals y. Okay, so x, y, and yx in the relation implies x equals y. So what essentially does this mean? Well, let's first analyze a couple of examples, and then let's go through and try to pick at this a little bit further, because I think of all the properties, the antisymmetric property is probably the one that's the hardest to understand. So let's do a couple of them. We have, again, let's go back to the relation that we love, the less than or equal to 1 on the integer z. So let's analyze this. So is this an antisymmetric property? So let's see, here is our definition for all xy. We can say x is related to y, so x is related to y, and y is related to x implies that x equals y. Now, if I tell you that two numbers, x and y, that x is less than or equal to y and y is less than or equal to x, is the guarantee that x equals y? I think so. I think that's the guarantee. And there is another proof here. I'll let you think about how you would prove this one. There is a very nice mini proof here along the lines of how we proved the last one. So think about it, how you would prove this. But this is actually true. So we'll just say this is antisymmetric. Okay, and if I tell you two numbers is x is less than or equal to y and y is less than or equal to x, the only way that can happen is x is equal to y. Okay, so we'll just leave it at that, and we'll say because this is true. Okay, this is a true statement. All right. What about a counterexample? So let's take a look at another relation. So the one that we had before, xy such that x is congruent to y mod 5. Okay, so let's take a look at this one. Again, this one is on z. So can we say this is antisymmetric? Well, let's look at the definition. For all xy, if x is related to y and y is related to x, does that guarantee that x equals y? Well, you can see that obviously this is not going to be true. We saw many examples in which x is congruent to y and y is congruent to x mod 5, but x and y don't have to be equal. So here's a counterexample. We can say 3 is congruent to 8 mod 5, and 8 is congruent to 3 mod 5, but this does not imply that 3 equals 8. Okay, so this is not antisymmetric, and this is because this is false. And there's our counterexample there. Okay, so what can we take away from this? What is the definition of antisymmetric? Let's concentrate on the counterexample first, and then maybe we can derive a good a definition in English what antisymmetric actually means. Anytime we can find two items, two elements, x, y, which are both related to each other and they are different, then right away we can say this is not antisymmetric. Okay, so again, if we can find xy and yx and they are both in the relation, right away you can say that it is not antisymmetric, right? Because the only way that those two things can be related to each other is if they are the same. Okay, that's the rule. So another way to look at that is that if you have a relationship going one way, you better not have a relationship going the other way, right? So if you have xy, you better not have yx. That's basically the English definition of antisymmetric. Okay, now just to go back and to make a quick note of transitive. So earlier we talked about transitive statement. The transitive statement is the one where we said x, y, y, z, therefore x, z, right? And we didn't really give a counting formula for transitive property. And in fact, we're not going to, because there's no such counting formula. So given, you know, the size of A, how many transitive properties are there on A, it really, there is no equation for that. However, for antisymmetric property, there is an equation for that. So let's go back and let's go all the way back to this one. So so now let's talk about the number of antisymmetric. Let's use purple this time. I want to find the number of antisymmetric relations on A. Okay, now let's start with our example that we had before. So what we saw in the symmetric relations was we grouped them, right? We grouped AB, right? So we grouped AB and BA. We also grouped CA and AC. So we also grouped those two. And then we also grouped BC and CB. And we said in this case, there was 3 squared minus 3 of these, 3 squared minus 3 divided by 2 of these groups, right? Because they're paired off, there's only 3 of these groups. Now, let's pretend that we want to create an antisymmetric relation. Now, let's think about the group AB and BA. Now, from the group AB and BA, what can I choose out of those elements so that it is antisymmetric? Now, try to keep in mind that antisymmetric means if I see AB, I better not see BA. Right? That's our English definition. Now, can it be true that we don't include either of them? And the answer is yes. I could leave out both of those pairs if I wanted to. Okay, so let me explain again. If I'm looking at this group, okay, the group AB and BA, one possibility is I can put in just AB. That's one possibility. Another possibility is I can just put in BA. And a third possibility is I leave out this group altogether. Okay, so instead of giving 2 choices, there's now 3 choices for that group. Okay, so for AB and BA, there's 3 choices. For CA and AC, there are 3 choices. And then BC and CB, there are 3 choices. So again, take one of the pairs, take the other of the pairs, or don't take any of them at all. Those are our 3 choices. So if we take a look at the this, we would get the equation 3 squared minus 3 over 2. Now, just to generalize a little bit, well, let's talk about that later, actually. You can probably guess what the generalization is. But the last thing I want to talk about here is what about these AA, BB, and CCs? Can I include those in an antisymmetric relation? And the answer to that is yes. They're actually the same as any other pair. So if I include AA, and by the way, I don't need to, right? For it to be antisymmetric, I don't need to. So if I include AA, I could, or I can leave out AA. Same with BB, same with CC. So here we have another 2 to the 3 choices for the anti-symmetric relations for the objects that are in the form of XX. Okay, so just to let you know, these are the objects in the form XY. These are the objects of the form XX. I hope you understand what I mean by that. Okay, so so I think we're good. There's really no other way that we can simplify this equation. So I guess we can generalize this. If it's n, then we get the equation 3n squared minus n over 2, again, because we have n squared minus n over 2 of these xy groups. There's 3 choices for each one of those groups, and then there's 2 to the n of the xx's. Okay, so just try to keep these equations in the back of your mind. There might be a chance that I can ask you about these types of equations. So just keep them in your notes and just know them. Okay, so again, let's review very quickly what our properties are. So first we have a reflexive property. Reflexive property means X is always related to X. Symmetric property means that anytime I have XY, I will have YX. Transitive property means XY and YZ implies that I have XZ. And then antisymmetric property means anytime I have XY and YX, they must be equal. X and Y must be equal. Now, let me just elaborate a little bit on the antisymmetric property because some of you might be a little bit confused with this. Why is it that I don't need to include AA, BB, and CC in my previous example? Well, this says that if I see XY and YX, then they must be equal. Okay, but if I don't see x, y, and y, x, then there's nothing we need to say, right? So that's why this is saying that it's optional. So the object AA, BB, and CC are optional, right? We don't need to include them. Okay, so another thing that I want you to see is that the symmetric property, the transitive property, and the antisymmetric property are all in the form of implies. Okay, so these are a little bit different from the reflexive property because the reflexive property is just for all x, xx has to be there, right? That's the only requirement. I don't care what else is there, right? As long as xx is there, it is reflexive. Now with symmetric, transitive, and antisymmetric, it depends that the premise is true, then the conclusion has to be true as well. So for example, in the symmetric property, I need to see xy before I see yx, right? So if I don't see xy, then I don't need to see yx, right? So just keep that in mind as we evaluate these properties even further. Now, on a side note, a little bit later on, we're going to talk about this thing called partial orders and equivalence relations. Okay, so partial orders and equivalence relations. Partial order, the first thing that I want to introduce here is a relation that is reflexive, antisymmetric, and transitive. Now, if you look back in our slides a little bit, you'll notice that we've already given one example of that, which is the less than or equal to relation. Right, the less than or equal to relation is in fact a partial order because if you check back, it's reflexive, it's antisymmetric, and it's transitive. Right, that's the only requirement. There's another one called equivalence relation where it is reflexive, it is symmetric, and it is also transitive. Now, again, we've actually seen an example of this earlier, which is the congruency relation. Now, just try to convince yourself, like the mod x is congruent to y mod 5, that relation. So try to convince yourself, because we didn't really actually do this one for all of the properties. So try to convince yourself that this one, in fact, is an equivalence relation. We'll talk a little bit more later on in this topic about what is so significant about equivalence relations. All right, but before we do that, I want to introduce this thing called a directed graph. So a directed graph is a way that we can represent a relation that is on a finite set. Okay, so if we have a finite set, now not infinite sets like integers, right? Integers is an infinite set. A finite set would be something like 1, 2, 3, 4, right? So if I have a finite set, I can draw a directed graph just to allow us to be able to visualize what's going on in our relation. So for example, let's say I give you a relation like this. 1 is related to 2, 2 is related to 3, 2 is also related to 2, 3 is related to 4, and let's say 3 is related to 2. And this is a relation on A. Okay, let's imagine that. So we can translate this into a graph. Now, first of all, I want you to convince yourself that this, in fact, is a relation on A. Okay, so I want you to convince yourself of that because it is a subset of A cross A. Okay, so just convince yourself that R, in fact, is a subset of A cross A. So how do we draw such a directed graph? Well, firstly, what we need to do is plot all the points that is represented in our set A. So I take set A, all of those elements, and I just put them somewhere. It doesn't matter what order they are. It doesn't matter where they are. And I'm just going to write out all of the relationships. Now, when we see a relationship XY, that means there's an arrow pointing from X to Y. So for example, I see 1, 2. I'm going to draw an arrow from 1 to 2. I see a 2, 3. I'm going to draw an arrow from 2 to 3. I see a 2, 2. I see a 3, 4. And I see a 3, 2. Okay, so that's it. Those are all of the relations that I have. And now you might be asking, sorry, those are all the relationships, like the arrows that I have. Now you might be wondering, how is this an improvement on what we did before, right? Before we just, had R is equal to whatever, and then we can just analyze all of our properties. How is it that a directed graph is going to help us in any way? Well, the answer is they can help us to visualize all of the properties. Now, again, here is a good opportunity to do a quick recap or a summary of what we've talked about before. So, so what is reflexive? Reflexive means for all elements in A, for all elements in the set, that XX is there. X is related to itself. That element is related to itself. Now, just looking at this graph, let's say I had no idea what this is. Okay, let's say I didn't tell you what what this drawing was. Could you tell just from looking at the graph whether or not it's reflexive? I think we can, because a reflexive property graph would mean that there's these loops everywhere, right? So because this is not there, and this is not there, we can claim that this graph is not reflexive just because, for example, 1, 1 is not there. And so we can see these counterexamples really easily from looking at this graph. Okay, so I hope you can see the benefit of having one of these graphs. Okay, what about symmetric? What's the definition of symmetric again? Every time we see xy, we see yx, right? Every time we see xy, we see yx. So on the graph, what would that look like? Every time we have an arrow going one way, we must have an arrow going the other way. So is this symmetric? And again, the answer is no, this is not symmetric, because we have 1, 2, but it did not imply 2, 1. So again, visually, we can see this really quickly, because every time we have an arrow going one way, but no arrow going the other way, right away, we can say this is not symmetric. That is our counterexample, right? Now, you might argue, wait a minute. What about 2, 3, and 3, 2? That's symmetric, but is everything symmetric? Because what a symmetric property means is that everywhere in the graph, you must see returning arrows. Okay, now here's another point. I don't see an arrow between 1 to 4. Is that a counterexample for symmetric? And the answer is no, right? Because remember, symmetric means if I see 1, 4, then I see 4, 1. But I don't need to see arrows in between. Okay, so just keep that in mind. All right, next, is this transitive? Now, transitive is a little bit harder to see from the graph, but transitive basically means shortcut. Okay, so I see 1, 2. So you see the arrow 1, 2. I see the arrow 2, 3. Which would imply, if it was transitive, that I would need to see an arrow from 1, 3. I would need to see a shortcut. And here, I don't see a 1, 3. So right away, I can see it's not transitive. Now, I think we can play around with transitive a little bit, because there are many counterexamples here. So let's take a look at another one. There's an arrow from 2, 3, and there's one from 3, 4, right? So 2, 3, and then 3, 4. But I don't see 2, 4. Okay, so again, this is a good counterexample for transitive, because I would need to see that if it was transitive. All right, so what I want you to do right now is pause the video and think of one more counterexample for transitive. Okay, so we've come up with 2 counterexamples for transitive. Can you come up with one more? Now, realistically, we only need to come up with one counterexample, but this is a good opportunity for us to play around with the definition of transitive. So maybe pause the video right now. Try to think of another counterexample. All right, so here's the solution. This is kind of a difficult one. I see 3, 2, and I see 2, 3. So under the definition of transitive, what would I need to see? I would need to see 3, 3. The shortcut here would be 3, 3. Right? So if I have an arrow from 3, 2, and I have an arrow from 2, 3, then theoretically I need a 3, 3 as well. Okay, so this is another counterexample for transitive. All right, so hopefully you were able to figure that one out, but I'm just going to delete 2 of these, because realistically I don't need all 3 of these, but just take note of the last one, because the last one's kind of tricky. Okay, so the last thing I want to talk about here is antisymmetric. Now again, what did antisymmetric mean? What was the definition of antisymmetric? Whenever I see an arrow going one way, I better not see an arrow going the other way, right? That was antisymmetric. Well, here is our counterexample. Whenever I have xy and yx, they must be equal to each other. Here I see 2, 3, and I see 3, 2, but they're not equal to each other. So it's not antisymmetric either. So you can just see that in this relation, it turns out that it's none of those properties, which means that generally if I give you a relation, many times it will have none of those properties. Right, so it takes a really special relationship. It takes a really special relation in order to have all of these properties. Okay, so okay, I hope everyone is kind of happy at this point how we can be able to pick out these properties from the directed graphs. So this is just a kind of a description of what I just said. So I hope all of this makes sense. Let's do a few more examples just in case we want to we wanted some practice. So let's pretend that we have A, which is 1, 2, 3, 4. And I want to do a couple of exercises. So the first one that I want to do is let's draw a graph. So let's say I have an example like this. Okay, you're given this graph. Oops. Okay, so I want you to tell me, does it have each of those four properties? Is it reflexive? Is it symmetric? Is it transitive? Is it antisymmetric? Okay, so yes or no. And then if it's no, you should probably come up with a counterexample. Okay, now here's another relation. So let's talk about the relation xy such that x is less than or equal to y. So let's talk about that relation. And then let's see if we can graph it. Okay, so I want to graph it according to this definition. All right, so so maybe again, let's pause the video right now. You can work on this and see what you get. And again, I want to find out whether it's reflexive, symmetric, transitive, and antisymmetric. So I want to find out those things. All right, so, so let's look at the solution. Let's start with the less than or equal to. Now, the best way to draw such a directed graph is to start with each one of the points. Okay, so I'm going to start with the point 1, and I'm going to draw 1, 2, 3, and 4. Okay, so I'm just going to draw those individually, and I'm going to see where they land. Okay, so what is 1 related to? Well, 1 is related to 2 because 1 is less than or equal to 2. 1 is less than or equal to 3 and 4, and also itself. Okay, so the good thing about this is now we're done with 1. Okay, what is 2 pointing to? 2 is pointing to 3, 2 is pointing to 4 and itself. 3 is pointing to 4 and itself, and 4 is only pointing at itself. Now, of course, if our set was bigger, right? So if we had set 5, 6, 7, and whatever, this would be a bigger graph. But here we were only looking at the set 1, 2, 3, 4 because it is on the set A. I should have mentioned that. This is on the set A. Okay, so let's analyze each one. Is it reflexive? Is it symmetric? Is it transitive? Is it antisymmetric? So let's start with the first one. Okay, so these are two graphs that we can pick out these properties. So is it reflexive? No, it's not, right? Because it's missing 1, 1. So 1, 1 is not there. That's a counterexample. Is it symmetric? The answer is yes. Every time we see an arrow going one way, I see an arrow going the other way. So by definition, this is symmetric. Now, again, you might argue, well, what about 3, 4? There's no arrows between 3, 4. Well, we don't need it because the definition says if we have 3, 4, then we need 4, 3. Okay, is it transitive? No, it is not. And I'll leave this up to you to see if you can find a counterexample. There are actually many here. Okay, try to find one counterexample for transitive. Antisymmetric. So is it antisymmetric? Again, it is no. And again, if you remember the definition of antisymmetric, every time I see an arrow going one way, I better not see an arrow going the other way. Okay, otherwise it's not antisymmetric. So essentially, anytime we see arrows going opposite directions, it is not antisymmetric. Okay. What about the second one? Is it reflexive? Yes, because everything has a loop, right? Every element has a loop, so it's reflexive. Is it symmetric? No. What's a good counterexample for this? I'll let you come up with that. You can see actually there are many counterexamples here. Transitive, it is transitive. Okay, I'm just going to leave it at that, but I'll kind of invite you to look at every 2 arrows. Okay, so every time I have an arrow and then another arrow leading away from that, there's always a shortcut. Okay, so therefore this must be transitive. So for example, I see 1, 2 and 2, 3, and I do see a 1, 3, right? So that is transitive. Is it antisymmetric? And once again, it is, because every arrow is only going in one direction. I don't see an arrow going the other way, right? So it is antisymmetric. Okay, so I hope by now you're kind of comfortable with these properties. I do want to take one aside here and talk about let's go to a blank screen here. I'm gonna go back a little bit, sorry. Okay, so is there such a situation where I can find a relation that has all 4 properties? In particular, I want to analyze symmetric and antisymmetric, because those of you who are kind of really paying attention to the definition, you might be saying, well, those two seem like they're opposites. It seems like every time something is symmetric, it's not antisymmetric. And anytime something is antisymmetric, it's not symmetric. And in fact, that would be pretty close. Okay, so that understanding would be pretty close. But it's not the whole picture, because there are cases that have all 4 properties. So you can have one that is symmetric and antisymmetric, and you can have one that is neither, right? We already saw an example of that. If you look back a couple of slides ago, right, we saw an example that is neither symmetric or antisymmetric. So what about all four properties? Properties. Okay. In short, the only way that we can have all four properties is the following. Okay, which translates to this relation, the relation xy, where x equals y. This is called the equality relation. And this equality relation always has all four properties. So let's analyze. Is it reflexive? Yes, because it has all these loops. Is it symmetric? Yes, because 1, 1, 2, 2, 3, 3, 4, 4. Every time we have xy, we have yx. What about antisymmetric? Antisymmetric means every time we have xy and yx, they are equal. Yes, that's true. Right? In fact, there are no arrows in between any of them, which is kind of to our advantage. The fourth one is transitive. Is it transitive? Now, some of you might be hung up on this, but remember, transitive means if I see xy and yx, sorry, xy and yz, I must see xz. But here, I don't see xy and yz, right? So that means I don't need to see xz. So once again, it is transitive. Okay, so let's keep this in mind. It is that property unless you can find a counterexample. Okay, if you cannot find a counterexample, then it doesn't have that property. Then, sorry, it does have that property. Okay, so again, what I said before is it is transitive until you can find me a counterexample. So that means, can you find a xy, a yz that does not imply xz here? And the answer is I can't, right? Anytime these two are true, this will be true. Okay, so just try to keep that in mind because transitive is always one of the more kind of difficult ones to analyze in terms of coming up with a counterexample. Okay, so let's move on to the next idea. So we talked earlier about a partial order. Now, if you recall, a partial order is a relation that is reflexive, antisymmetric, and transitive. Okay, those three properties. Now, those three properties, it turns out, will give you some kind of nice structure to work with called a partial order. In fact, let me underline antisymmetric because this is actually the key to a partial order. Antisymmetric means it has direction. Okay, whenever you have an arrow going one way, it never comes back the other way. So that means the elements in your relation are somehow ordered in some way. Okay, this is why it's called a partially ordered set or post set. Now, for any comparable set, now as an example, a comparable set looks like this. So comparable set means the elements within our set can be compared in some way. Okay, so 1 can be compared to 3, 1 can be compared to 4 in its relationship. Okay, so we can say that 1, 2, 3, 4 as a set and the less than or equal to symbol is an example of a post set because the set along with the relationship together make up a partially ordered set. So if you look back a couple of slides, we said that the less than or equal to relation, this one right here, right, this one right here, is reflexive, it's transitive, and it's antisymmetric. So that makes it a partial order. So this is a partial order. Okay, now you might be saying, so what? So I don't see anything special about that diagram. Well, let's actually draw this diagram in a different way. So instead of drawing it as like this, right, as kind of like a circle, let's draw it with its corresponding levels. Now, if we're talking about the less than or equal to, so if we're talking about the set 1, 2, 3, 4, and we're talking about the less than or equal to relationship, then clearly you would agree that 1 would be on the lowest level. So I'm going to draw 1 on the lowest level, and then it would be 2, and then it would be 3, and then it would be 4. Now, these levels are not always intuitive, right? I'm just using the less than or equal to example as an example, right? Because it's so intuitive that 1 belongs on the lowest level. Okay, but what about how they're related? So if we draw the graph again, you'll see that 1 is related to itself. 1 is also related to 2, to 3, and also to 4. 2 is related to 3 and also itself. 3 is related to 3 and 4. Oh, sorry, 2 is also related to 4. Okay, and now I hope you can see a little bit better what we're talking about in terms of order. All the arrows in this diagram are pointing up. And in fact, 1 can always get to 4, right? It goes through all of the other elements to one of the higher levels. So it turns out that this directed graph, this digraph, can be drawn in the form of what we call a Hasse diagram. And a Hasse diagram has these levels, but all they have in between them are these straight lines. Now, in fact, if we call this a Hasse diagram, there is a hidden meaning of what these connections actually mean. So for example, in a Hasse diagram, it means that every point is related to. Now, remember what related to means. Related to means has an arrow pointing to, is related to all points above. So every point, we'll call it x. Okay, so every point x is related to all points above it, above x, that it's connected to. Okay, so I apologize for the terrible grammar here, but let me try to explain what this means in English. So every point x is related to, well, is related to itself and all the points above x that it's connected to. Okay, so what do I mean by this? Well, if I take a look at the number 1, okay, what is 1 related to in this relation? Okay, now let's pretend you don't even know what this relation is. Okay, so I don't know that it's a less than or equal to relation. What is 1 related to? According to this definition of the Hasse diagram, 1 is related to itself, right? 1 is related to 1, and it is related to all the points above it that it's connected to. Okay, so it's related to 2, it's related to 3, and it's related to 4. Now, let me go a little bit further and define what this connected means. Connected means I can get from the point x, I can get from x to the connected point only by going up. Okay, so the point is that on a Hasse diagram, I am only allowed to go up, I'm not allowed to go down. Okay, that's the single most important thing I want to tell you in the Hasse diagram. So if you remember nothing else, try to remember that. Okay, on a Hasse diagram, you can only go up, you can never go down. Okay, so what is 2 related to? 2 is related to itself, is related to 2. 2 is also related to 3. 2 is also related to 4. Is 2 related to 1? No, because we can't go down on the Hasse diagram. It's going up only. Okay, so 2 is only related to 3 and 4 and itself. Okay, what's 3 related to? 3 is related to 3, itself, and also 4. Right? So now the good thing is, if I just give you a Hasse diagram, you should be able to figure out all of the points in that Hasse diagram. Okay, but let's first do another example so that we can have a better idea of how these Hasse diagrams work. Now, before we do an example here, I want you to realize that in order for us to have a Hasse diagram, it must be a partial order, because if it's not a partial order, there is no Hasse diagram. Okay, so no partial order, no Hasse diagram. Okay, just remember that. What if I give you the set 4, 3, 12, and 24? And I tell you that I have a relation R, and I want to find out whether or not this is a partial order. So R is a relation xy such that x divides y. Okay, so I'm not using the normal straight line here, such that x divides y. Now, what does this mean again? It means that x times an integer is equal to y. Okay, so x times an integer is equal to y. So is this reflexive? Is it transitive? And is it antisymmetric? So this is what I want to analyze for the Hasse diagram. Okay, does it have all 3 of those properties? So let's start with reflexive. Is it true that x always divides y? X always divides x. Does it x divide itself? Yes, always. Right? X times an integer is equal to x, always. Okay, what about transitive? Now, transitive is a little bit harder to analyze, but if I tell you x times an integer is y times an integer is z, can we say that x times an integer is z? We can. In fact, there was a theorem that says exactly that. So if we look back at topic 4, we actually looked at one of those theorems. And again, there's a mini proof for this. So try to prove it on kind of on a side note. Is it antisymmetric? Now, antisymmetric, we have to be careful here. Look at these numbers that I've given you, 3, 4, 12, and 24. They are all positive numbers. They're all positive integers. And that makes it antisymmetric. So antisymmetric means if x divides y and y divides x, then x equals y. Right? So is it true for all the xy's? Yes, it is. Now, let's think about this. If I gave you a set of positive numbers, positive integers, we can claim that it is antisymmetric. Okay, so this relation on positive integers, it is antisymmetric. Okay, but what if I gave you this relation on the set of integers? Okay, now let's not even think about zero, because I think zero is definitely a counterexample here. But can we claim that it is antisymmetric? Well, the answer is no, it's not antisymmetric. Why? Because can we now claim that x divides y divides x means that x equals y? What about 1 divides -1? That's true. -1 divides 1. That is also true. But is 1 equal to -1? No. So that is a counterexample for antisymmetric, right? So 1 times an integer is -1. -1 times an integer is 1, but they're not equal. Right? So that means on a graph, you would see opposite arrows going both ways. So this is not antisymmetric, right? So that tells you one thing. If I have a property that's on a smaller set, like this set, like the set that we have here, or the set positive integers, it may have a property like antisymmetric. But if we make our set bigger, if we expand our set to something like integers, suddenly you might not see that property anymore. Okay, so just keep that in mind. That's going to be very important. Just because on a smaller set I see a property, it doesn't always mean on a bigger set I'm going to see that same property. Okay, so let me take away all of this. Okay, so I hope that made sense what I said there. But let's take a look at the Hass diagram for this. So we've established that this is a partial order, right? So it's a partial order. It is reflexive. It is transitive. It is antisymmetric. Now, can we make a Hass diagram out of it? So this relationship, it seems like 3 is on the lowest level. It seems like 3 is on the lowest. What is a what is a multiple of 3 here, right? So what does 3 divide? Well, the next thing that we can see is that 3 divides 12. So it makes sense that maybe 12 is on the next level. And then it makes sense that 24 would be on the next level after that. Now, remember our definition of Hass diagram. We said if you have a point, it is related to itself as well as all of the points above it that is connected to, right? So here we can see that 3 is related to 3, so 3 divides 3. 3 also divides 12, and 3 also divides 24, okay? Which is good. We still have that definition for the Hass diagram. But the question is, where is 4? Where does 4 go? Well, does it belong under 3? No, it doesn't belong under 3. It seems like it belongs in the same category as 3. And this is how we're going to draw 4. We're going to draw 4 in this way. Now, remember, it is only connected. Two numbers are only connected, or two elements are only connected if they are going up, right? So here we can say 4 is related to 4, 4 is related to 12, 4 is related to 24, which is true. But is 4 related to 3? No. Is 3 related to 4? No. Because at some point, in order for me to travel from 3 to 4, I would have to go down. And again, we cannot go down on the Hass diagram. Okay, not allowed to go down. All right, so I hope that makes sense. Now, let's add a few more numbers in here. What if I added the number 6 in here as well? Okay, where would the 6 go? Well, you can see that it would go between 3 and 6, 3 and 12, right? So 6 would actually go something like this. So now, is everything still correct? Is 3 now related to 4? No, it's not. Even though 4 is on a higher level, 3 still cannot get to 4, right? So under our definition, it is still not related. 3 is still not related to 4. 6 is also not related to 4. Okay, but what if I add a 1 in here? Where would 1 go? Well, 1 is divisible by 3 and by 4. Sorry, 1 divides 3 and 4. So 1 would be on this level, connected to both 3 and 4. All right. So I hope you start to see what this, how this Hass diagram kind of goes. Okay. So let me do maybe one more, a couple more quick definitions, and then we'll go on to the next section here. Right. So the next thing we want to talk about are called maximal and minimal elements. Okay, and we're also going to talk about greatest and least elements. Now, these things are all pertaining to partial orders. Okay, so these things are all pertaining to partial orders, meaning that we have something like this. So let's give our definition from before. We have how did the Hash diagram look? So we had 3, we had 4, we had 12, and we had 24. Okay, so let's take this as an example. Let's take another one. Let's take this one as an example. A, B, C, D. Well, let's actually just do A, B, C, D like that. Oh, actually, no, we shouldn't do that. It looks exactly the same as the other one. Let's do E and F like that. Okay. Now, before we move further, let's take a look at the second Hash diagram here on the right. Now, if I just gave you this Hash diagram, would you now, given our definition of the Hash diagram, would you now be able to tell me all of the ordered pairs of this Hash diagram? Okay, so look at the Hash diagram, A, B, C, D, E, and F. Could you now tell me all of the pairs in this partial order? Well, you should. I hope you're able to tell me, because the definition is that every element is related to itself and everything above it. So the first question is, what is A related to? A is related to A, it's related to C, D, and E, but not F and B. Okay, verify that you understand what I mean by that. Okay, so A is related to A, C, D, and E, but not B and F. Okay, what is B related to? B is related to C, D, E, but not F and A. What is F related to? F is related to F and also E. Okay, so what we're going to see, for example, is FF and FE. All right, we're going to see AA, AC, AD, AE. Now, try to complete this list. Okay, for every one of those elements, can you tell me what they're related to? Okay, so try to finish off this list. All right, what else do we have here? Okay, so let's analyze the maximal and minimal elements of each set. Now, maximal and minimal, right, means that they don't have to be unique. Okay, they don't have to be unique. So what maximal means that you're at a point in the Hash diagram in which I cannot go up anymore. Okay, the official definition of maximal is the only thing that it's related to is itself. Okay, the only thing that it's related to is itself. Now, for the first one, the maximal element would be 24. In the second one, the maximal element would be E. Okay, so let's verify. What is 24 related to? 24 is only related to 24 in this Hash diagram, nothing else. What is E related to? E is only related to E, nothing else. Okay, so that makes it maximal. Okay, now I did mention that maximal and minimal elements do not need to be unique. So let's give an example. What if I had another one like this? What if I had a G like this? Then G would also be maximal. Okay, so please verify that. So if I had G there, G would also be maximal. But as it is, it's only E. Okay, what about minimal? Minimal means there's no element that's related to it other than itself. There's no element that's related to it other than itself. Okay, so in our first example, it's 3 and 4. Let's verify. What's related to 3? Only 3. What's related to 4? Only 4. Okay, the only thing that's related to it is itself. Okay, what about the minimal elements for the second one? Well, the answer is A, B, and F, right? Because F, the only thing that's related to F is F itself, right? Just verify that. Nothing else is related to F. Now, when I say related to, it means that, right? So something is related to F. That means F is the second thing in this pair. So you can see that for something to be minimal, it doesn't need to be on the lowest level. It could actually be on, second highest level, right? That could happen. Okay, now let's talk about greatest element and least element. Greatest element and least element. The greatest element, the official definition is every other element is related to it. Every other element is related to it. So the greatest here is 24. And the greatest here is E. Now, in short, if there's only one maximal, then it must be the greatest. Okay, just remember, if there's only one maximal, it must be the greatest. Similarly, if there's only one minimal, it must be the least. Okay, if there's only one minimal, then it must be the least. If there's multiple minimals, then there's no least. Okay, greatest and least means it's unique. Okay, now the official definition, once again, of greatest is every other element is related to it. The definition of least is that it is related to every other element. Okay, it is related to every other element. That is the definition of least. So, let's take a look here. Why is 24 the greatest element in that Hass diagram? Well, because 3 is related to 24, 4 is related to 24, 12 is related to 24, and 24 is related to 24. So that's why it is the greatest. Okay, now I know these are just definitions for now, but when we come back, I'm going to take a look at, I'm going to go a little bit further with these definitions and take a look at some applications for maximal and minimal elements, as well as greatest and least elements pertaining to the partial orders. Okay, so when we come back, I'll get into that. So see you in the next video.